Welcome back, class. In this video, we're going to talk about phase diagrams and various properties of liquids. So let's start off talking a little bit about phase diagrams. So my focus here is really for you just sort of understand what a phase diagram is and be able to sort of name the basic parts of a phase diagram, to locate the different phases in a phase diagram, and to sort of do basic navigation of a phase diagram. So what a phase diagram is designed to do is to give you a single picture of under what temperature and pressure conditions the various phases of a material exist. And so this way we could look at different temperature pressure combinations and figure out what phase or phases of matter are going to be present. So let's look at our phase diagram for water as our sort of typical phase diagram. So the regions, right, are where the states represent. So typically in most phase diagrams, the solid is going to be on the left hand, sometimes the upper left hand, depending on the exact phase diagram of the phase diagram. Now, in this middle section, sort of between these two lines, is where liquids is going to be. And then the gas phase is going to be more toward the lower right-hand side of the phase diagram. Now, the lines that separate these phases go by names that sort of talk about the phases that are along that. So, first of all, the liquid-gas line, or the line separating the liquid from the gas, is called the vaporization curve, or sometimes called the vapor pressure curve. Either of those two terms are fine. So the vapor pressure curve or the vaporization curve. Now, anytime you're on a line, we have both phases existing simultaneously. So these are where phase changes are coming, right? So as you cross over those lines, you're undergoing phase changes. Now, certain materials have what's called a critical point, and this is going to be the end of the vapor pressure curve, the utmost vapor pressure curve. And this is where, if present, we'll see what we call the supercritical fluid. So the critical point defines the critical temperature and the critical pressure. So you can see here, the critical temperature is here, the critical pressure is here. So remember what I said, that once you're at this temperature or beyond, right? So in this region here, no matter how much more you increase the pressure, right, you can never go back to the liquid from the gas, right? We can't go back to the gas phase once you're in this supercritical. There's no phase change line, right? You're just in this supercritical region, right? So increasing the temperature is not going to get you to go from a supercritical fluid into a gas, right? So you're in this supercritical fluid phase in the phase diagram. Now, the other lines, the line separating the solid and liquid phases, right, is called the fusion curve, right? For melting, right? So the fusion curve. And the line separating the solid and the gas region is the sublimation curve. Okay, so we have names for the curves, obviously names for the phases, and we've seen the critical point. One other important point on a phase diagram is where the three lines intersect. That's called the triple point, and that defines the temperature-pressure combination where all three phases can exist simultaneously. So where you can have all solid, liquid, and gas existing simultaneously at the triple point, right, the 1 point. Now, I am going to point out something that's a bit weird about this particular phase diagram, so that when you see others, you don't think that they're somehow strange. notice here that the fusion curve for water has a slope. It slopes back to the left. So what this is implying, right, is that as the pressure goes up, the melting temperature gets lower. For most substances, the freezing point will increase as pressure goes up. So most materials will have a fusion curve that has the opposite slope, if you will. So water is unusual, and this again goes back to the fact that water solid is less dense. And so that this is manifest in this sort of different kind of fusion curve. So just a little statement about this particular one for water is a little bit different than some of the others you might see. So in terms of working with this phase diagram, we're going to be, you can, pick particular, I want to say pressures. And as you read across, wherever you cross a line, that's going to represent a phase change. So when you cross between solid and liquid across the fusion curve, if you drop down, well, you should reach the melting point. And when you cross the vaporization line, right, the vapor pressure curve, you should see where the boiling point is. Now, notice water doesn't sublime readily under normal pressure conditions, right? Now, doesn't mean it doesn't, but we don't see it subliming very easily here. But not all phase diagrams look identical, right? Every material has a little bit, different phase diagram. So let's look at a couple other phase diagrams. So these are iodine and carbon dioxide. So these are materials that more readily sublime, and they just, pay close attention to the scales on the two axes to sort of see what's going on here. So for iodine, notice the triple point occurs, at 114 and like 1/10 of an atmosphere. Okay, so fine. At 1 atmosphere, you can see that iodine will melt, but not until you get to 114 degrees. It will boil or will vaporize at 184 degrees. But if you raise the pressure of the iodine, it will transition, let's say at 184 degrees, it'll go from a gas to a liquid at higher pressure. You increase the pressure even more, you can get it to solidify. And so we can see what the effect of, changing temperature, changing pressure, what phases it allows me to go through, right? You can increase temperature and you can look at the phase changes. You can increase pressure and look at the phase changes that occur. I will also point out the normal sloping fusion curve here. CO2 is nice to look at because we can see, under sort of normal conditions that we readily cross the sublimation curve. Right? So we cross sublimation curve at minus 78 degrees. And notice, as long as you're at normal atmospheric pressures, CO2 never melts, right? It never crosses the fusion curve, right? You can't get CO2 to melt unless you're at very high pressures, well above 5 atmospheres of pressure before you can see liquid CO2. And so, every material has, a different phase diagram. You can see they have sort of similar shapes and, characteristics, but all are going to be unique as well. So again, what we want to be able to do is to do basic phase diagram naming, parts, regions, points, and be able to do basic navigation on a phase diagram. Okay, so let's turn our attention now to talking about some basic properties or some sort of common properties we associate with liquids. So the first thing is something called miscibility of liquids. And this is the mixing of liquids, kind of like solubility, but with a little different twist here. So miscibility, right, is the ability to mix liquids without separating into two states. So you can take the two liquids, mix them up, and you become one, right? They don't separate into two states, or what you might call two liquid phases. And this is going to depend, at least partially, on the attractive forces that the two liquids, what we'll call the solute and the solvent here. Now, these particular terms, I'm not going to get so hung up on them right now, the solute and the solid. If you take Chem 2, we'll get much more into this in Chapter 14 when we talk about solutions. But we talk about the liquids here, the attractive forces between the liquids, and how strong those are going to determine a lot about the miscibility. Now, the driving force, or sort of our big saying here, is like dissolves like. And so this is based on polarity, right? We first talked about this back when we talked about soap in the last chapter, chapter 11, where we looked at how soap molecules work to make nonpolar grease or oils soluble in water by acting to bridge these, right? So even though oil is nonpolar and water is polar, by using those soap molecules, you could get them to dissolve. But normally, right, polar likes polar, nonpolar likes nonpolar. Okay. One other general point about miscibility is if two liquids are miscible, they will be miscible in all proportions. So they'll always be miscible, whether you have 5% of one and 95% of the other, or 95% of the one and 5% of the other. So they mix in all ratios. So polar substances like to dissolve other polar substances. They have what we call hydrophilic groups, right? So you'll see a lot of oxygens here, a lot of H's, right? So we got OH's, we got CO's, CO double bonds, carboxylic acid groups. Some other groups that you might not see on there are, ammonia groups, NH bonds, right? Chlorides. These are going to be things that can tend to make things polar. Now, nonpolar molecules will like to dissolve in other nonpolar molecules, and these are going to be things that are what we call hydrophobic or water-fearing, right? They don't like water. And these molecules are going to have a lot of carbons and hydrogens, right? A lot of CH bonds, a lot of CC bonds, a lot of carbon and hydrogen floating around there, or in these molecules. Now, as we mentioned with soap, and soap are not the only example here, is that many molecules are large enough that they can have separate hydrophilic or water-liking or polar regions, and water-fearing or non-polar hydrophobic regions. And so sometimes this can make them be soluble in both polar solvents and non-polar solvents. Or, it can allow them to act like soap and to allow polar and non-polar materials to mix. But basic idea is polar likes polar, non-polar likes non-polar. And so here we can see a couple of obvious examples where we get a hydrocarbon like pentane and water. You can see here that the two things just will not mix, right? Oil and water, same idea. Now, what's the basic reason here? And I'm just going to put it in a little different way than what we have here. And it's a matching of the intermolecular forces. So remember, polar molecules can have dipole-dipole and hydrogen bonds, right? which are basically the same kind of interaction. But they can have that particular kind of interaction. Nonpolar molecules cannot. They can only have dispersion forces. So if you have a nice polar molecule, like water or some other polar molecule that can have nice, stable, pretty strong dipole-dipole interactions or hydrogen bonds, what you're asking them to do if they mix with a nonpolar is to give up those stronger interactions for most likely weaker dispersion forces. And so it's just not going to do it, right? You need materials that can have sort of a matching of the intermolecular forces. So if you have two polar molecules, they can both do dipole-dipole. So that means they can dipole-dipole with each other. And so that allows them to mix and form, sort of similar type intermolecular forces that they have when they're by themselves or when they're pure. A nonpolar, same way, right? They can form dispersion forces with each other, just like they would if they were in their pure state. So we get a good matching of the intermolecular forces. And that's really more than anything what's determining that these things can exist. And that's the or mix. And that's the basis of that whole like dissolves like idea. Okay, so let's talk about some other properties. So first of all, surface tension. So surface tension is the phenomenon that we can get things that are more dense, like a steel hook or a paper clip, and we can get them to float on a less dense material like water if we do it very carefully, right? And this is because the liquid has what we call a surface tension, right? And this is the property of a liquid that results from a tendency of liquids to minimize their surface area. So this means that those molecules want to get as close together as possible on the surface to minimize the surface area. This causes a rounding, if you will, but if we have a big enough surface, we don't see the rounding like we see in, say, a drop of water, right? Where if you make a sphere, right, it's going to minimize the surface area. And so, but the idea is these surface molecules want to get as close together as possible. Now, the reason for that is that these surface molecules behave a little differently than the interior molecules because of what are called cohesive forces. And so you have cohesive forces on the surface molecule between other surface molecules and the ones below them. But it's unequal because there's nothing above them. They're not surrounded in 360 degrees by other molecules, other same molecules, like other water molecules. And so the pull on them is unsymmetrical. So we have a net pull in toward the center. And so if we take all of these surface molecules and we sort of pull them in toward the center, they're going to get smushed closer together. And so the surface area acts like a skin, if you will. And even more so, maybe a little bit of an elastic skin where you can put little divots in it before you break through. So you can push on the surface, cause the surface to deform a little bit before you actually break through the intermolecular forces that are holding those surface molecules to each other. And this allows something like a paperclip to float on water. Now, if you go to that paperclip and you poke it hard enough to where any little bit of it punctures the surface tension, that paperclip will immediately sink all the way to the bottom, right? Because the interior molecules have uniform pull all around it, so they don't have the same kind of surface tension. It's just a matter of, if it's more dense, it can break through those intermolecular forces. And again, we see this phenomenon in water all the time, right? Where they likes to form perfect spheres. Well, in the absence of gravity, it's a perfect sphere. In the presence of gravity, it's more like a drop, an elongated sphere. But it wants to minimize that surface area. So if we look a little bit more closer at this phenomenon again, so these surface molecules that have fewer neighbors, right? Let's say 4 here. They're going to be pulled toward the interior, right? And so if all of these molecules are pulled toward the interior and toward each other, that's going to squish those surface molecules together. They have a higher potential energy, right? Because they're not equally acted upon on all sides. And so the surface tension builds up, right? And it's the energy that's required to increase the surface area by a given amount. So once you increase the surface area by a given amount, then you will break through. So you think about putting a little divot that stretches everything like it's a skin. And you poke that skin, it stretches, and eventually it spreads apart. It rips. And that's the idea with surface tension. So the surface tension is going to be linked to how strong the intermolecular forces are. So water has pretty strong intermolecular forces with its hydrogen bonds. It develops a pretty good size surface tension. And these are both at room temperature. Whereas something like hexane, a nonpolar molecule with dispersion forces, has a much smaller surface tension. So if you take something like hexane or pentane or gasoline, right, you're never going to get a paperclip to float on there because of the much lower surface tension. So the stronger the intermolecular forces, the higher the surface tension will be. Now, of course, like a lot of things that involve intermolecular forces, temperature plays a role. So if you raise the temperature, you raise the energy of these molecules, it allows the molecules to move faster and faster, makes it easier to stretch, right? And so as your temperature goes up, the surface tension decreases. And so the surface tension of hot water is going to be less than the surface tension of cold water. Now, another common sort of property of liquids that we think about is something called viscosity. So viscosity is a liquid's resistance to flow. So when we think about liquids, they flow, which means the molecules roll past each other, if you will. Kind of like thinking about if you put a ball covered in Velcro on the other part of the Velcro and just try to roll it up and down, right? There's a resistance there. And there's the same kind of resistance when molecules flow along each other. So they're still connected by intermolecular forces, but they're breaking intermolecular forces with one molecule, making it with the next one, and breaking it and making it, breaking it, making it. And that allows them to move by one another, but still be connected. And so the higher the resistance to flow, the higher the viscosity. Now, don't worry so much about the units, right? This is just giving you the units. So if you see numbers, right, you know that we're talking about CPs. Those are centipoise, right? And so water is sort of the standard. It's 1 centipoise at room temperature, and everything else is sort of relative to that. Again, intermolecular forces are going to play a role because you're breaking and making them as you go. So the stronger they are, the harder it is, the higher the viscosity. So liquids with stronger intermolecular forces are going to be more viscous than ones with low intermolecular forces. The more spherical, so shape plays a little bit of role here. The more spherical the molecule is, the easier it rolls by each other, the higher the lower the viscosity will be. More long, skinny molecules are going to have higher viscosity because they have more surface contact, right? They don't slide by as easy. They even so much we might call get tangled together, right? These long, skinnier molecules. So if we look at various liquids here, and these are again a series of hydrocarbons that get increasingly bigger, right? So more mass, longer and skinnier molecules. Remember, as the mass goes up, the dispersion forces go up. So we have higher intermolecular forces as you go down here. So the intermolecular forces are increasing as you go down. The viscosity increases as well. Okay, so this is the idea. So higher viscosity, higher intermolecular forces, higher viscosity. So temperature, like a lot of things with intermolecular forces, again, are going to have an effect. So raising the temperature, again, makes the molecules more energetic. They have more motion. They're easier for them to break the intermolecular forces, right? They already have more kinetic energy, and so they can flow easier. So when you heat something up, the viscosity goes down. So take something that has pretty high viscosity like motor oil or maple syrup. Maybe, as you heat it up, it becomes less viscous, right? Easier to pour, higher flow. So water, now, not that you can really notice the viscosity change in water, but it becomes much less viscous when it's at high temperature than it is at room temperature. Okay. So, last thing we're going to look at is this phenomenon called capillary action. And this is the ability of liquids to flow up a tube against gravity. So, the narrower the tube, the higher the liquid rises. So, if we look over at the diagram, water won't flow up these pretty, large tubes very far. These skinnier tubes, capillary action allows it to flow much higher. Okay, so what's going on here? So, what we have is the competing, or maybe say even the working together, of two types of forces. We have cohesive and adhesive forces. So let's define them. So first of all, cohesive is the forces that hold the liquid molecule together, right? So these would be our intermolecular forces, right? So these are what's holding the molecules together, what's making them cohesive, right? Like a group. Adhesive forces attract the liquid to other surfaces. So like adhesive tape, right? Holds something to each other, right? So the adhesive forces are what holding the water to the tube, if you will. So in this particular example of capillary action, the adhesive forces pull the liquid up the sides of the tube, right? Because the liquid, if it's attracted to the surface of the tube, if it has strong adhesive forces, it's going to be attracted. That's going to pull it up the surface. The cohesive forces allow the bulk, the liquid, to be pulled along with it. So this allows the water to, as a whole, rise up the tube. Now, of course, it'll only rise until it meets gravity, right? So it can overcome gravity to a certain point, but then if you take, the amount of liquid in this tube, right, and it has a mass, and when that mass gets high enough that the force of gravity, becomes, enough, right, it's not going to rise anymore, right? So as you're pulling more and more mass up, as it rises higher and higher, eventually gravity wins out and it can't rise anymore. Now, of course, the narrower the tube, the higher, because as the narrower the tube, you have the same mass of liquid here, just distributed over a longer stretch of the tube, because, the volume in the diameter is going to be less, right? So this might represent the same volume as this, but it rises higher in the tube. So capillary action. Now, different liquids are going to behave differently. Water, right, or most commonly with, right, has pretty strong adhesive forces to glass, right? And so it rises up quite nicely. Right? And it pulls the water with it nice because it has pretty nice, cohesive forces as well. But those things work together. Now what that results in is in a glass tube, water forms what we call the meniscus, this classic meniscus where it's concave, right? Which means the adhesive forces are stronger than the cohesion. So water is highly attracted to glass. Glass has polar components in it, right? So that water is nice and attracted to the glass even more strongly than it is to itself. And so it tends to creep up the sides even a little bit further than what it can pull it up through capillary action. So you get this meniscus that's concave. Now if you put mercury, a liquid that is nonpolar, right, it doesn't have very good attraction to the glass at all. And so the cohesive forces are stronger, and so you get a convex meniscus, right? Where the fact that the cohesive forces are a little bit higher causes a bubbling, if you will, or push-up of the liquid in the middle and a weak adhesion onto the glass. And this, of course, because those, in this case, metallic bonds that are holding the metal together are stronger than the intermolecular forces between the mercury and the glass. Now, this behavior is going to be different depending on, the tube as well, right? If you put water in a plastic tube, you would see a different meniscus, right? In a plastic tube, water is going to have the convex meniscus because water's not attracted to plastic in the same way as glass. Plastics are typically nonpolar, and so you don't get those really strong adhesive forces, so you get a different kind of meniscus. So, just some unique survey of some of the ideas when we talk about liquids. All right, so we're going to wrap that up there, and this actually wraps up what I want to talk about in Chapter 12, but as I mentioned, I'm going to talk a little bit about one specific part of Chapter 13, and we'll do that in the next video, focusing on some types of solids.